Hello students, in this lecture I would like to discuss some definitions and examples of ring, finite, infinite, order of ring, rings with zero divisors, rings without zero divisors. So with the examples we can analyze those definitions. So as I told you that in this lecture I will discuss these finite, infinite rings, units in a ring, zero divisors in a ring with examples. And what are the learning objective of this lecture? The objective of this lecture is to understand the basic concepts or definitions of finite and infinite rings, order of ring and zero divisors. Examples to interpret the above definitions also. And first we shall take finite and infinite rings. So we shall see the definition of this finite and infinite ring. If the number of elements in a ring R is finite, then this R is called finite ring. Otherwise it is infinite ring. As I told you that if the number of elements are finite in a ring, that ring is we call it as finite. Otherwise it is infinite. Means number of elements are infinite, uncountable. Examples of these finite and infinite rings are set of rational numbers, set of real numbers, set of complex numbers, or all infinite rings. Since these rings of these are infinite. The rings of matrices M to R is a finite ring. The ring of real continuous function is also finite ring. And then consider any finite set, then its power set with respect to symmetric difference as a first operation, and set of intersection, so it treated as second operation, which is an example of a finite ring. So matrices over any ring makes a ring. Taking finite ring as your scalars, we get a new finite ring of matrices. And what is the order of ring there? The number of elements in a finite ring is called the order of the ring. As we know that finite ring, the number of elements in a ring is finite, that is a finite ring. And order of ring is the number of elements in a finite ring is called a order of ring. Example for this is the ring of matrices M to R is of order 2 there. That is a order of a ring that 2 there. And next we shall see the definition of units of a ring with unity, that is the identity element with respect to multiplication. The non-zero element which holds inverses under multiplication are called units of a ring. Means any non-zero element which satisfies the inverse axiom under multiplication, which is called the units of a ring. That is, for any non-zero element which is a member of R, there exists another element that is also non-zero, which is also member of that system ring, such that A dot B, product of A dot B equal to B dot A is 1. That is the units of a ring with the unity. Another example there, in the set of all integers, we have minus 1 into minus 1, that is 1. Therefore, 1 is a unit but not a unity of the ring. So, since it is minus 1. So, in the set of integers, 5 elements in that. So that units are 1, 2, 3, 4. That is, we note down this. Unity is nothing but multiplicative identity, which is also a unit, but every unit need not be a unity that. Keep remember that. Unity is also unit, but converse need not be true. Every unit need not be unity that. So next we shall see the definition of rings with the zero divisors. Any non-zero element, suppose if I take A of a ring, R is said to be zero divisors of R if there exists another non-zero element in that system such that A dot B equal to 0 or B dot A equal to 0. Means what here? If you have an element, if R is commutative ring, then non-zero element is also in that R is called zero divisors. If there is another non-zero element which is also non-zero, keep remember, such that that product is also 0. That we called it as a ring with zero divisors. Keep remember here, you have an element in a ring which you want to say that zero divisors. If there exists another element which is also non-zero element such that product of that to this element is 0, that we called it as a non-zero element in a ring R. So that is that is nothing but it is a zero divisors of R. That. And examples of this zero divisors of R. Suppose if you take a 2 and 3 in the system, integer system with element 6, so those product of 2 and which is since 2 and 3 are non-zero elements, but this product of these two, 2 into 3 and 3 into 2, it is again which reminder that is 0. So that is what 2 and 3 are zero divisors of Z6. And 4 is also zero divisor of Z6. Since it is also because if you take any 2, that is also elements, its product is 0 there. So that is what. And if you take these two matrices 0, 1, 0, 0 and 1, 0, 0, 0, 0. But since by taking individually it is non-zero elements, non-zero matrices. But the product of these two matrices, it becomes a 0. That's why these two matrices are zero divisors of M2 of Z. So we notice that number of divisors of product of two integers of order m and n respectively, that always can be taken it as that is order of product of these two order minus that is the order of a ring there, order of a ring, so m and n minus 1. So that's why since it is this one, because if you take a union of these two, union of product of these two is nothing but magnitude of individually that. So that is what it is in this one, phi of m into phi of n. Since this is Zn is a finite ring with a unity there. And that set of matrices, set of all 2 by 2 matrices, just to take let us take A is this non-zero element, non-zero matrices, B is also non-zero matrices. If you take a multiplication of these two, it becomes 0, then wherein A and B are non-zero matrices such that product of these two are 0, therefore this matrices is a ring with zero divisors. So similarly you can take another example that also that is these two A and B are non-zero elements. As I told you that here in previously we have discussed in previous slides, so that Z6 in which 2 and 3 are zero divisors, because product of these two, this reminders may be 0 that either 2.3 and 3.2 is 0 that. So that reminder is 0. So that is what here. And you take, as I told you, one is 0 and this is again it becomes 0. So that is A is only zero divisor of that. So that is what. And 4 is zero divisor in a Z12 in as there exist 3 in Z12 such that, because since there is 12 in 3, factors of 12 is 4, 3 or 6, 2 there, but in which we are saying that 4 is 0 divisor, so that 4.3 is equal to 12, that's remainder is 0, so that product is 0. That is what 4 is 0 divisor in Z12. And you take any non-zero matrices of that product is 0. So then those two are non-zero divisors. And now we shall see the rings without the zero divisors definition. The ring which do not obey that definition, or which is not a zero divisors, so which is called without zero divisors. That is, if you take any two elements in the ring R wherein that product is 0, but that implies that either A is 0 or B is 0, or else both are 0. So at least one of them may be 0. That product is 0, but thing is that it is not a zero divisor. That is what. Let us take just system R equal to Z, real number equal to that Z. The units are here -1 and union of these two. There are no non-zero divisors. Keep remember, there are no non-zero divisors. So that's why, because its product is non-zero, so that it is that also. It is non-zero, no zero divisors. So what are the outcomes of this lecture? After learning of these concepts, the students will be able to understand the concepts of finite, infinite rings, examples of a ring, finite and infinite rings, and rings with the unity and without unity definitions and examples, and zero divisors and without zero divisors, and also we can analyze these definitions through an example. So thank you.